Thank you. Thanks very much, guys. Happy to be here again at the DPDK Userspace Summit. Today, we want to welcome you to our session about P4 enablement in DPDK. I guess the key message that we want to send to people today is that you don't necessarily have to develop your application from scratch. One other way that you could do is you could simply write your application in the P4 language and get DPDK code generated for you under the hood. Trying to move to the next slide. Let's, yeah, sorry about that. It seems to be an issue with moving to the next slide. So, as many of you know, we have been working for quite some time at this point to enable people to run their P4 programs on multi-core CPUs using DPDK. Right, for those folks that are still new to P4, P4 is actually a language. It's a language to describe data plane processing in terms of tables and actions. It also has a companion called the P4 Runtime, which is essentially a message passing protocol on top of gRPC to allow the configuration plane to manage the tables, get statistics, do any other configuration updates that it needs to do. We have made quite a bit of progress up to now, and we now have a data plane engine in DPDK that is P4 programmable, essentially the pipeline library and some other libraries that are dependencies. And we also have this data plane engine from DPDK driven by the P4 compiler. P4 compiler, which is called P4C, is an open source compiler. We tend to use to call this activity of enabling P4 in DPDK. We use it simply P4. We call it simply P4 DPDK. Which is essentially an open source project to run P4 programs on multi-core CPUs. There is also a project called IPDK that uses P4 DPDK as the CPU target. This project allows other targets to other P4 targets under the same control plane API, and we use P4 DPDK as the CPU target. And we have two main components. There are actually more repositories. I have a slide to list all the main repositories that are collateral to or are associated with the P4 DPDK. But the main two are the open source P4C compiler from p4.org and data plane engine, which is in DPDK. So I just mentioned this project called IPDK. IPDK stands for Infrastructure Processor Development Kit. Essentially is an open source project, a framework rather that allows managing the infrastructure offload, and it is basically enabling multiple targets under the hood, multi-core CPUs, IPUs and DPUs, and also switches, programmable switches. And here is where P4 DPDK is used as the CPU target for this project. I definitely encourage people to take a closer look at IPDK on ipdk.io. This is the list of repositories, all in open source, that are associated with P4 and DPDK, and probably other targets from the IPDK project. I'm not going to go through this list is just put here for convenience, so people can later on refer to it easier. This slide basically presents an update of the features that we implemented since last year, since we presented P4 DPDK last year at the DPDK Summit 2021. The gray boxes are the ones that we already had at that time. There might be improvements, but not a major redesign. And the blue boxes are the ones that represent the new features that we implemented in the last year or so. So I think this illustrates the fact that we did do a lot of work recently. Maybe this is a good slide to illustrate why we need P4 DPDK. I hear people asking this question lots of time, like, why do we really need to write our data plane in P4? We have DPDK, we can simply code our application completely in C or C++ using the DPDK libraries, maybe other libraries as well. Why do we need yet another data plane project, and why do we need this language? Well, the answer is that essentially, as you see, for data plane, it's quite fast to do a quick prototype to just move packets around. But in order to build a comprehensive data plane or a complex application, you also need to have many other components. Like you need to have tables to do lookups, you need to have actions, you need to have meters, counters, registers, checksums, you need to have I/O ports, and you need to have mirroring, you need to have a CLI, you need to be able to map easily your code to different cores and scale up with the number of cores. So many things here that we have defined in the P4 language, and we are also working to enable in DPDK for use with the P4 language, right? So, for example, what we did in the last year, we enabled LPM table lookups. We had the wildcard match tables. We had the exact match table. We also enabled two table types that don't map very well to the classical table model. In the P4 language, tables are typically read-only for the data plane. The data plane can just do lookups and just get data from the tables, but cannot change the tables. It is the control plane that manages the tables, adds entries or modifies entries or deletes entries. Now, this is why in order to, for example, to increment a counter for packets or bytes, you need a special object, which is read-write by the data plane. Is called a counter or is called a register, depending on how you want it to work. Also, meters fall in the same category. And also these two tables, the action selector is essentially a table for ECMP, is for example, when you want to map your next, you want to map your route to a group of next hops and just pick any of the next hops in that group rather than have a single next hop. So that's why we call it a group, and we have to select that. And we also have to select the same next hop all the time for all the packets that belong to the same flow. I have a slide on this one coming up. Also, the add-on miss table is a table that is read-write by the data plane. The data plane can decide to add the keys, to add new entries to the table. Essentially, when you do a lookup and you have a miss, typically you could decide, you could run some logic there, conditional logic to say, hey, you know what, I want to add this table, this key that I just missed on lookup, I want to add it to the table with this action and this action parameters. This is very useful for connection tracking. The classical P4 model is in order to learn a new connection, a new flow, you would send the packet that missed the table, you'll simply punt it to the control plane. But sometimes the loop required for the control plane to just go analyze this packet and update the table is too long. It might be even longer than the connection lifetime. You might just have a very short-lived connection, just the TCP SYN, ACK, SYN, ACK, and just some a few packets and then the fin packets to terminate the connection. So then it's not feasible to rely on the control plane to do that. So that's why we have this add-on miss table that we also implemented in DPDK. And we also made a lot of progress on how the C code is generated for the pipeline. We had a model that we used to call interpreted mode, where we didn't generate C code. I think in 21.11 DPDK release, we added this capability to replace that so-called interpreted model with C code generation that could be built up by the C compiler and get much better performance because of the C compiler being able to see your entire code for your program rather than just see some small snippets of code that we call instructions and we run under the hood. So yeah, also it's important to realize I've seen a lot of people that are able to build data plane prototypes really fast to do things simpler or more complex depending, but they totally neglect the control plane interaction. So we should not forget that we also need to be able to manage these tables, add entries, delete entries, update entries in various tables, also update the meters or read the counters or write the counters from the control plane sometimes, like when we need to reset statistics. And all these things have to be done by the control plane, ideally without stopping the data plane. Obviously, it's easy to just stop the data plane while the control plane updates are taking over. But during that time, what happens is that if that time is too long, which is typically the case, I mean, it would be prohibitive to build, for example, a wildcard table, an ACL table, to update it because it requires you to rebuild that table from scratch. So obviously, you cannot simply stop and rebuild, take seconds to rebuild that table or even more, right? So you have to keep the data plane going while in the background, the control plane is creating a new copy of those tables. That's what we do in DPDK. We have a main copy and a mirror copy for each table. We have the control plane to update the mirror copy, and then the control plane will swap the tables with the data plane, and the control plane will update what used to be the main copy, which now became the mirror copy. Now, one thing to highlight here on the table updates, which is over here, atomic table updates, it's here in DPDK for a while, but it's very important. I keep talking about it. It's to realize that the way we do things is simply we swap a pointer on a packet boundary, and that pointer is a pointer to an array with all the table handles. So in order to update tables, there is a sort of transactional process going on where the control plane could, or the user could ask the control plane to add more or various new entries on different tables. The control plane will do that in the background, and then when everything is ready, it will try to commit those changes by simply swapping a single pointer that contains the handles for all the tables, right? So you could atomically update multiple tables at the same time. So that's very important, and that requires a lot of work. The code, the effort to write the control plane code or the table update part is actually more than to update the data plane. So that's yet another strong reason to avoid writing your application from scratch and try to use a framework like P4DPDK, where you could get all these things for free and you could connect them in very complex topologies very quickly. That's what this is about. It's about building network stacks on the CPU very quickly. In terms of the toolchain, how does P4DPDK really work? We actually cleaned up a lot our toolchain. There are still things to be done here. Essentially, you start by writing a P4 program. That should be much smaller. It's a description of your data plane. Should be a much smaller effort than actually coding everything in any language. And that P4 program goes through the P4 compiler, the open source P4 compiler. That compiler produces a file that we call pipeline.spec from specification. And the difference versus the P4 file is that the compiler basically removed all the syntactic sugar like enumerations, nested control blocks or functions, and also translated the action code, the imperative code of the action, which is pretty much conditional code with if, then, else, for example. Same also translating the main program, which is the life of the packet, which says it describes what the packet should do from the moment it is received by the moment it is transmitted, essentially doing some parsing, doing some table lookups, basically calling all the tables in the process. So that part gets translated to a sort of assembly, a P4 assembly, if you want, which is in this spec file. We call those instructions, very small snippets of code that update some internal structures. So we used to actually take this spec file and load it in our DPDK application or in the DPDK pipeline library and simply run out of the spec file. What that means is that for each of those instructions, there is a predefined function that is going to be called the C function. But that is kind of not optimal because the GCC, the C compiler or CLang or any other C compiler only sees those individual instructions, individual functions associated with the instructions, very small pieces of code that and can optimize only those small things in isolation. So what we did in 2211 and what we are working to improve now, there is a patch pending. We removed this interpreted mode where we simply call a function for each instruction, and we are generating C code. So the pipeline library is now generating a pipeline.c file. What this file has is it has a single C function for every action of every table. And it also has some C functions associated with the main subroutine of the program, the so-called life of the packet that I just mentioned, which explains what the packet should do from reception all the way to transmission. So we have a few functions there. It's not a single function for the program. It's multiple functions for a reason that requires more detailed explanations. It's mostly related to table lookups, which we try to kind of work with multiple packets in parallel. So it's a sort of yield that we do on table lookups and on other instructions because of memory reasons, prefetches, so on and so forth. So then basically everything that could be executed in one shot, all those instructions that could be executed in one shot, we wrap them into a function, but you could have multiple functions that are essentially what gets executed between the tables on the main path of the program. So once we get this C file, basically this represents your entire application. Under the hood in that C file, you'll see that all the previous instructions that used to be in the spec file now became an inline function into these functions that I mentioned. So now the C compiler can see the whole program, the C code for the entire program, and will do a way better job to optimize everything. And hence, we get a performance improvements between 30 to 100%, depending on what the program is doing. Right, that's what we were able to see on some of the use cases that we have. But of course, some other people might have a different experience. Your mileage may vary. So then, obviously, the C compiler will compile this, will build this C file into a library. It's a shared object library, and this is the new representation of the P4 program that the DPDK library will load at runtime. So all this process obviously is an offline process. Currently, some of these steps are part of a sample application. We want to improve that and make a new application just to control all this build process. Stay tuned for a next patch in patch set in DPDK. What happens at runtime, right? Essentially, we have an SDN controller over here, which is external to your data plane node. The data plane node could be anywhere connected through the network with the external controller. It's your server probably. And the external controller, the SDN controller, will get this pipeline.so file, and it will send it through the P4 runtime protocol to a target agent running on the data plane node on your server. And that target agent, which right now is the pipeline application in the examples folder of DPDK, which is doing a lot of stuff, maybe, I mean, well beyond what an example should be doing. This will load this shared object library. It will build all the data structures for the pipeline. Then we map that pipeline to one of the CPU cores. We can run multiple pipelines on the same core. We can run different pipelines on different CPU cores, and we can connect them through I/O ports, right, like rings, or we can connect them through tap interfaces or through Ethernet devices, right? And then the SDN controller will simply just perform table updates through P4 runtime, and it will also read statistics periodically, right? This is how the whole system is working. A few details about some of the use cases that we enabled with the latest changes that we mentioned. Some of these tables, some of these use cases were very difficult to enable previously. So for example, connection tracking is using that add-on miss table that I mentioned. This allows the data plane to modify the table entries without any control plane intervention. The entries will expire automatically. They will expire on timeout. There is a timeout associated with each entry when the entry is added to the table. If that entry is hit before it expires, you have the option to rearm the timer with the same value, with a different value, or simply do nothing, in which case that entry will expire naturally whenever the timer will go to zero, right? This could be changed, right? If you have yet another hit later on, even if you decided on the first hit to do nothing, later on you could decide to, based on your code, conditional code, to actually rearm the timer for that entry and keep it in the table. This is very useful if, for example, you want to implement a TCP state machine for connection tracking, right? The default action for this table is to learn the missed flow, the missed entry, right? Conditionally, you could decide not to learn it if you don't want it. And on the regular action will simply have to decide whether it wants to rearm the timer or do nothing. We also have a complex example here. I put the link to the P4 program in case people want to take a look at this Linux networking program that we recently open sourced. Another example is the VX Land Encapsulation, where we simply have a table with 64,000 tunnels or more, and we get the input packet looked up into this table, and we get the tunnel details, basically 50 bytes of headers, outer Ethernet, outer IPv4, outer UDP, outer VXLAN, that we need to prepend to the packet. We also need to update the lengths of IPv4, the total length of IPv4 and UDP, because this cannot be pre-computed in the table. It needs to be, it depends on the input packet. And we also update the checksum. So this is yet another good example, and it's one of my favorite to benchmark the performance of our P4 DPDK tool. Another one is a complex FIBA routing table or forwarding information base with virtual routing and forwarding support, VRF support, and ECMP, WCMP support. Essentially, a VRF means that you could have multiple routing tables, multiple logical routing tables or virtual routing tables, one per customer maybe, or per tunnel, or per application. But they are all melted into the same physical routing table. So the lookup key for this table, for the routing table, is not just the IP destination, which is an LPM match field. it's also this ID of VRF that needs to be an exact match ID. And essentially, this is the logical routing table within the physical one. And then we use this action selector table that I just mentioned for ECMP support, where we have a group of next hops that we associate with each route in the routing table. And we select next hop. We do some hashing based on an n tuple that the user specifies in order to preserve packet ordering within the same flow. And we send the packet out. So in conclusion, I think it's fair to say that we did a lot of work to enable P4 DPDK in the last year. We definitely encourage people to use P4 DPDK to develop complex CPU network stacks and see the performance for themselves. I think they will be very pleased. I also encourage people to take a look at the IPDK project on ipdk.io. And we hope to continue to grow, become better, faster, and more pervasive with every year and every every DPDK Userspace Summit going forward. Thank you very much, and open for questions now.
Hey, we've got a couple of questions here.
Hi, you mentioned that you were able to improve the update performance using P4 from, you said, from around 20 to 100%, if I'm not mistaken. So P4 is a general language, and it eventually wraps the RT Flow API. So RT Flow API gives you many options that you basically abstract. You have an abstract in P4 that hides it. So how are you able to get better performance?
I'm not sure. Is this sorry or can you recommend yourself? Sorry,
Alex.
I didn't catch. Alex. Okay, hi, Alex. Yeah, what I said is probably two things. I'm not sure if there is a confusion or not. What I said is because of the C code generation process that we do, we get a data plane improvement between 30 to 100% in terms of throughput packets per second.
So not the update.
What I also mentioned is that we have a special update mechanism which allows us to update the tables without stopping the data plane. Mm-hmm. This is not actually related to P4. I mean, it's related to the implementation rather than the P4 abstraction. P4 doesn't really say much about the table update, but it's probably important on any target, whether it's a CPU or whether it's an IPU, DPU, or whether it's a switch or an FPGA or a NIC. It's important how fast can you update these tables, and it's important to do the updates in parallel with the data plane without stopping the data plane, which causes packets to be lost. So that's what I mentioned. This update process also allows us to increase the update rate, essentially because this update is happening on the mirror copy of the tables, and it's happening on multiple tables, and then it's very fast. We just swap a pointer, right? So you could simply wait for update requests for different tables for, let's say, 1 millisecond or 10 milliseconds, right? You don't need to basically commit immediately the first update, because you have some tables, especially in software, the wildcard table requires it does not allow incremental updates. So if you want to change anything, either remove one entry or delete or add a new entry or update an existing entry, you need to rebuild the whole table from scratch, right? So which is a very lengthy process. So by simply batching, I mean, the same things that we do on data path, which is we batch multiple packets together, right? We do the same thing on the control path now. We batch multiple requests for update together on different tables. We update those tables with all the requests we got for the last 10 milliseconds, right? And then we simply swap one pointer. So that allows us to be much faster in terms of update rate as well, because we can batch potentially thousands, millions of requests in the same update. Probably unlikely, right? But we can batch as many as you get in that time interval that you accept, right, for batch. Does this make sense?
Yeah, thanks.
Now, in terms of RT flow, RT flow is our DPDK API to update the tables. In terms of P4 runtime, there is a different kind of mindset here, I would say, because the mindset of P4 is that no protocol is predefined. We don't know what Ethernet and IPv4 are before they get defined. So the way P4 runtime mostly works is you define, the P4 runtime knows the format of the key of the match in a table in a generic way. It knows that there are this many fields, and it knows the size of each field, and it knows the match type of each field, whether it's an exact match, basically the mask of each field, right? And we don't refer to those fields in terms of protocols like, oh, this is IPv4 or whatever, this is destination IP. No, this is just field number 5 in the match set of fields, match and tuple, right? And on the data side associated with the key, we simply talk in terms of the action that got predefined. We say associate this action that was previously defined in the P4 program, which may only be only exist for this current P4 program, is not predefined like or hard coded there in firmware or anywhere, right? And we also provide so basically action ID and the value for each action. Action parameter that is required for that action, right? So if you have an encapsulation action, you need to provide typically value for some protocol fields, right? And you say, okay, here is the value for outer header, outer IPv4 header destination address, right? And all these things that are part of the action itself, now you have to provide. So that's how P4 runtime works. There is probably straightforward to do a translation from RT flow to P4 runtime. But the other way around, I'm not that sure, right? Because of simply of this difference that P4 runtime is protocol agnostic, while RT flow is having all these predefined protocol fields there. So it would be great if we could also evolve RT flow to maybe add some more agnostic methodology to specify the match fields and the more action-oriented methodology to specify the actions, right? Somehow, if we could have an action ID and let's say a generic way to specify the action parameters, that would be great, rather than have them predefined. So that's something food for thought for the RT flow folks.
Hi, so my question is regarding the MIS table. So last time I checked, the P416 spec didn't have such a thing as a MIS table, right? So is it, how is this extension implemented as a opaque function call?
That's a great point, yeah. So there is a specification, if you go to p4.org/specs, there is a specification for the P4 language. And some of these objects that I mentioned are not in that specification. Now, there are other two more specifications. One is called PSA, Portable Switch Architecture, and the other one is Portable NIC Architecture. And we do a lot of work on PNA currently. These specifications basically are a sort of the equivalent of standard libraries in the C language, right? So it's a way to extend the language to define new objects that are valid within that namespace of the architecture, right? So the add-on MIS table is in the PNA specification. If you go to the PNA specification there on p4.org, you will see a full description of this. For example, for the action selector, that's defined in the PSA specification.
All right, thank you.
Hi, Cristian. We have an online question again from Govink. Can P4 compiler control hardware offloading, generating C code, including DPDK RTE flow instructions?
No. On the P4, in the P4 world, I guess the accepted way to do offload is simply to take the P4 program. You see, the P4 program becomes a new abstraction, which is way more elegant than any C API. It takes a long time. We all know it takes a very long time to evolve a C API. And we need to add more things, and yeah, it's a very convoluted process and time consuming. Now, if a language it's also an abstraction, but the language changes way less often because it has a specification, it has a number of keywords, and that's it. So the way to offload things, for example, you have a P4 program. You can run it on the CPU, and let's say you want to offload it to a SmartNIC or an IPU or DPU, right? What you do is you don't really have to bifurcate code internally and define an interface, an API to do offload. All you have to do is say, fine, I'm not going to run this P4 program on that CPU target. I'm going to move it to the SmartNIC, IPU, DPU target, right? So now basically your hardware needs to have the ability to accept a P4 program that would decide what that hardware should be doing, and also the ability to expose the tables to the P4 runtime protocol, so that you could also get the programming of tables through the standard protocol without having to write new drivers for every piece of hardware, right? That's the beauty of RT flow. It's a standard interface, it's generic, it doesn't change. For example, if you add support for a new protocol in your hardware, you simply need to, the interface for the driver doesn't change either, right? So that's the way to do hardware offload or infrastructure offload. You simply move the P4 program to a different place rather than move some portions of a program running on the CPU or some elements of it, trying to send them to a different hardware device. So this simplifies things a lot for the offload discussion, in my opinion.
Yeah, Cristian, it's Thomas.
Hi, Thomas.
Hi. Different answer to this question is that I agree P4 is very portable, and probably we can also use a different compiler which directly translates P4 to RT flow. And I know that there are already some ongoing effort in this direction.
Yes, yeah, that's very good. What I would suggest is that, again, it would probably be easier to do this translation if we could also do some work to extend RT flow, to introduce maybe some new extensions to have generic match fields and generic actions with generic parameters. It would be much easier to do that, and it will be much more in sync with the P4 runtime, and it will probably benefit RT flow longer term, right? Because all these things, what we introduced in RT flow 5 years ago, might not be that useful now, or we might want to maybe deprecate some of that part, right? So it will be more stable if we make it more generic. But yeah, I agree. It's something very valuable that needs to be done.
Yeah. Well, one more comment. You are mentioning IPDK, and now you know it's getting merged in a project called OPI for open.
Yes,
yeah.
That's a very good point. So there is a project called OPI with many vendors, including Intel, including NVIDIA, including Marvell, including other folks, right? And IPDK, as far as I know, is a project or a sub-project within OPI, right? That's the current strategy. So yeah, I definitely think it's a good thing to have a broader ecosystem with all the vendors to make the market bigger, right? The data plane market bigger, the networking market bigger, rather than just focus on small little things that like a specific vendor can optimize because they are, let's say, opportunistically good at whatever that thing is. It's probably better to unite and build a larger ecosystem and a larger market for the benefit of all the vendors, which I think is one of the goals of OPI.
Yeah. Any other question in the room, maybe? Okay. Cristian, as expected, we are over time. And you know that's why your talk is just before the lunch. That's fine.
I'm sorry, folks.
No, that's fine. We meet you here, Cristian.
Yeah, hopefully soon. Yeah. Thank you very much, guys.
Thank
you.
It was
a pleasure. Bye.